coming to Theory Lunch. I kind of want to say that everybody knows John Wright, but in case you don't know John Wright, he's a grad student here until around 2016 maybe. And then he went to MIT for a 3-year postdoc. And now he's newly moved to Caltech for a postdoc. And eventually he'll settle as an assistant professor at UP Austin. And today he'll tell us about his talk's best paper winning paper. Thanks, Rob.
Yeah, the title of the talk is NEEXP is an MIP star. This is joint work with Anand Natarajan, my co-author. If you've never met Anand, this is what he looks like. And I'm just putting him up there to tell you that he's on the job market this year, so you should hire him. It's going to be a complexity class, or complexity talk, about like quantum complexity classes. But to kind of motivate what we're looking at here, I'd kind of like to rewind a bit to complexity theory some of the decades ago. So back to the like 70s and 80s, just to kind of see what were people looking at in complexity theory, what questions were motivating them back then. And so back in the 70s, the most basic question was the following. First question is going to be, what can a prover prove to a verifier? This is one of the most basic questions in all complexity theory. And the way we like to model this is the following. We have some verifier who has some language L that they'd like to compute. So they have a certain input X, they want to know if it's in the language, but unfortunately the verifier may be like a small polynomial time machine, very weak. Maybe the language L is a very complicated language, difficult to compute. And so what we do is we augment them with the help of a prover. And this prover is imagined to be all-powerful. And the way the prover and the verifier are allowed to interact is the prover is allowed to send the verifier one-way communication. And we conceptualize this as a proof pi. So this message contains a proof pi, which proves to the verifier that X is in the language L. And as we all know, this is like the complexity class NP. And just to make it a little concrete, instead of like a language L and a general input X, let's just consider like a three-colorable problem. So maybe the verifier has a graph G, wants to know if it's three-colorable. And so the proof that the prover provides to the verifier is just a three-coloring of G. Okay. So even though the verifier is like not powerful enough to compute this three-colorable itself, with the help of a prover, an all-powerful prover, it can still be convinced that the graph is three-colorable. And so the answer to our question of what can a prover prove to a verifier is, well, we don't know. We don't know what FP equals to. Does it equal P or not? This is like the major open question in complexity theory. So after this, we moved to the 80s. And in the 80s, people decided to augment this picture a bit. And so they started asking, what can a prover prove to a verifier with interaction? So you have the same kind of setup as before. You have a verifier, who wants to know if an X is in the language L. You have a prover, all powerful. But now instead of all communication going from the prover to the verifier is allowed to ask questions to the prover. So it can send messages in the other direction. And whenever it asks a question, the prover has to respond with some sort of answer. The two of them are allowed to go back and forth for as long as needed until the verifier is satisfied that either yes, input X is in the language L, or maybe it's not convinced, and so it says no, X is not an L. So this is the complexity class IP for interactive proofs. And we kind of know, yeah, we do know what it's equal to. So due to work of LKM and Shamir in the early 90s, they were able to show that IP equals P-space. And since we generally believe that P-space is a much larger class than NP, this shows that adding interaction to prover verifier scenarios actually significantly improves the power of the verifier. All right, so that was the second question. And at this point, you can pretty much do, like, you've added interaction, why stop there? What about two provers? What about three provers? Seven provers? So now let's just consider the case of two provers. So you have a verifier, wants to know if X is an L, but now instead of just one prover, there are two on either side of it. And for this talk, we'll call these provers by their standard names of Alice and Bob. And the crucial thing in this interaction is that the provers are not allowed to talk to each other. They can only communicate through the verifier. So a protocol here might look like the following. Maybe the verifier asks Alice a question, gets back an answer. Based off of the answer, asks Bob a question, gets back another answer. And so on and so forth. They kind of continue this for a while until at the end the verifier again is satisfied either yes, x is an L, or no, x is not an L. And this is a complexity class multiprover interactive proofs. I should say, like, what's the power of having two provers? Well, since they're not allowed to communicate to each other, you can ask two different questions to the provers. You can send one question to Alice, one to Bob, and Bob won't know the question that Alice gets. Alice won't know the question that Bob gets. So it makes it difficult for them to synchronize their strategies if they don't know what the other person is saying. And as a result, and also in the early 90s, it was shown that we got a characterization of MIP in terms of NX. Okay? So this is due to work of Bavai-Portnow 1. And what is NX? Well, it's the exponential time version of NP. So it stands for non-deterministic exponential time. This just means this is NP where the verifier is allowed to run in exponential time rather than polynomial time. And in NX, instead of asking questions like, is a graph recalculable, you ask questions like, is an exponential size graph recalculable? Okay? So much more difficult problems. And yeah, so what does this mean? Yeah.
Is that two provers and three provers the same thing?
Yeah, for MIP, yeah. So this is a complete characterization of MIP, and MIP is defined for any number of polynomial provers, but they showed that even if you just have two, you can do that.
So I don't actually understand this example. So what's the given exponential size graph?
Yeah, you mean, how do you formally define that? Yeah.
There's an input, and I'm supposed to decide something about it.
Sure, so I'll say that on the next slide.
Okay.
Yeah. So yeah, I haven't said exponentially sized graph as an input, not very well defined. So what do we mean when we say an exponential sized graph? Well, we mean the problem 16th degree coloring. And 16th degree coloring, your input is a circuit C. So a Boolean circuit C, which encodes a graph G sub C on 2 to the n vertices. And how does it encode this graph? So the circuit is going to look something like this. We'll have some number of input wires, and they're grouped into two sets of size n. So two input registers. The circuit itself is sized polynomial n, so it's small, it's efficiently representable. And if I want to know if an edge in my graph is, if a certain edge is in my graph, well, I take my vertices, and since there are 2 to the n vertices, they are in 1-to-1 bijection with the strings 0, 1 to the n. Okay, so each vertex has an n-bit encoding. And what I do is I just put the first vertex u into the first n-bit wires, and the second vertex g into the second set of n-bit wires. And if this circuit outputs a 1, then I say that u comma v is in my graph g sub c, and if it outputs 0, then I say u comma v is not an edge of the graph. Okay, so this is just like a canonical way, a simple way that's completely done at representing exponential sized graphs, but representing them in a way that a small polynomial time verifier can hold on to them.
Well, presumably you can't show that this is complete.
You can.
You really, this is.
Yeah. Yeah. So yeah, I'll get to that in 1 second. But yeah, so your problem here, you're given a succinct encoding of an exponential sized graph, and your goal is to output yes if the very large graph is recallable. All right, so yeah, this is NX complete. In general, for many of the NP complete problems, there are these succinct versions of them which are known to be NX complete. And like I said last slide, because we know that MIP is equal to NX, two provers can actually convince you that this exponential size graph is recallable. And it's kind of crazy because this graph is so large, you can't actually read the graph, right? You can't see, you can only maybe query a small number of edges in the graph. But in spite of that, the power of two non-communicating provers is enough to allow you to convince yourself that it's recallable. All right, so summary of 70s, 80s complexity theory. NP, don't know, IP equals P space, MIP equals MX. And you know, this wasn't just like fun and games, it's like very serious research. Back then it was kind of motivated by fundamental questions of what does it mean to prove something? What is a proof? And yeah, what different sorts of proofs give you different sorts of powers? But these questions are also responsible for like a lot of the very basic research that drives complexity theory to this day. So just to throw up a couple of them, yeah, two research areas that are still big today that rely on a lot of this line of work. One of them is delegated computation. So if you want, I don't know, Amazon to compute something for you in the cloud, but to verify that they computed it correctly, a lot of that work is a descendant from this line of work. And also the hardness of approximation, which one of the large theorems in there is the PCP theorem, kind of the foundational theorem of this area. And the PCP theorem is like a direct descendant of MIP equals NX.
Can I ask you an annoying question?
Yeah.
Like your first bullet point, you're like, oh, NP, it's unknown, it's question mark, question mark.
Yeah.
The third bullet point is like, NX is known, like, we're satisfied with
Yeah,
the
yeah.
answer. So.
Yeah.
Can you reconcile that?
Not really. I just expect someone to ask me that. Yeah. So at least the other two classes we have like characterizations of them in terms of like similar classes that we
Just joking around.
Yeah.
No, but I mean, in this context, there is an answer. It's just that one has to prove, right?
Yeah. It's equal to NP.
Yeah. I mean, yeah, it's just like this is some notation thing, right? That all these characterizations are just saying they're equal to some proven system.
Yeah. Yeah.
So John, I guess you could say that NP equals PCP log n.
I guess so. Yeah. Yeah. Yeah.
Okay, so I have one question, just to make sure I understand. So it's when you think about these two separated provers, probably you do think about them as having some shared information, just not something that depends on your question. Like they have some common coloring, for example, but they're
Yeah.
distributed.
So they both. You imagine that like they both see the graph ahead of time, and maybe they can sit in a room and work out their strategy.
Right.
But then the second the game begins, they're separated.
Okay.
And when we do it in the physics scenario, we actually imagine they're separated by many light years. Yeah, and then they're not allowed to communicate. So, all right. So that was the old 70s and 80s complexity theory. But you know, we're in the 2000s and later, and everyone's got a quantum computer these days. So we should just give quantum computers to the provers and verifiers. So there's like a canonical way we do this in like complexity theory, which is you take these complexity class names and you put Q in front of them. So you get that. But actually this doesn't work for like two of them, which is somewhat annoying. So QNP is actually the class QMA. QIP is correct, that's what we call it, quantum interactive proofs. And then QMIP is a class, but not the one we're going to be talking about today. So QMIP you should really be thinking of that as MIP star. And you can ask the same set of questions for these classes, and you get pretty much the same set of answers. Yeah?
What does it mean to give a quantum computer to something that's already all powerful?
Yeah, good question. We'll see that in a few slides. Yeah. So QMA, you can ask like, I don't know, what do we know about these classes? And it's pretty much the same thing. QMA, we don't know. QIP, also equal to P-space by Jane et al. And you know, if you didn't see the title of this talk, you just like look at this and you guess probably MIP star is also equal to NX. But if you guess that, you'd be wrong because we don't know what MIP star is. So this is like one of the major open questions in quantum complexity theory. All right, so what is MIP star? So MIP star is a complexity class for Alice and Bob. The provers themselves are quantum. So what does that mean? So we imagine before the game starts, Alice and Bob are sitting together in a room, maybe in a lab, and each one of them constructs a quantum state. So some sort of each one of them has their own personal qubits, which I'm going to represent with these like yellow dots. They can have as many qubits as they want. And what they're going to do before the game starts is they're going to do some sort of operation on their qubits to entangle them. Alright, so each of their states is now entangled with the other state. And I won't really go into what entanglement means, beyond just saying that it's some weird version of correlation. So it's some quantum-y version of correlations. Alright, so after doing that, they're fully done. And so what will they do? They'll separate, okay? Go to different rooms or different sides of the galaxy, whatever you prefer. But even if they go far away, their states remain entangled. This is a property of quantum mechanics. It doesn't depend on the distance. All right, and how do they interact with their states? Well, if you're quantum mechanical and you have a quantum state, you interact with it via a measurement. And a measurement is just some quantum thing where you perform a measurement, and whenever you have a measurement, it gives you an outcome. Yeah, that's what happens. You measure it, you get an outcome, and based on that outcome, you learn something about the state. So now, what does an MIP star protocol look like? We introduce our verifier. It wants to know if X is in a language L. And unlike the provers, which are quantum, the verifier is just going to be classical. consider this class where the verifier is also quantum, which means it has a quantum computer. Maybe instead of sending bits as messages, it sends qubits. But it turns out that class is equal to MIP star. And so for simplicity, we just assume it's classical. Okay, so the verifier wants to know if X is in a language L, and it will send a question to Alice. It'll send another question to Bob. And now Alice, having seen her question, will perform a measurement on her state. And she'll receive an outcome, and based off of the outcome of her measurement, she will reply with an answer. And similarly, Bob, who's received a question, will perform a measurement on his state. And based on the outcome of that measurement, he'll reply with an answer to the verifier. And again, the verifier will accept or reject based off of these answers. And the advantage that entanglement gives these provers is that even though they're separated, they can use these weird quantum correlations to somehow correlate their answers in ways that they wouldn't be able to do classically. That's all I'll say. Yeah.
So how does this compare with MIP with shared randomness?
Good. So MIP with shared randomness turns out it's just equal to MIP. So shared randomness doesn't help provers. And the reason for that is the following. So Alice and Bob, they have their shared random strings. But when they pick a shared random string, one of those shared random strings that they could get would actually be the best one. So condition on one of those shared random strings, they'll convince the verifier with higher probability than any of the other ones. So they might as well just fix that shared random string in advance.
John, one quick question. So here, if I did not allow the provers to be entangled, then it can only increase the power of the complexity class, right? Because I'm restricting the ability of the provers to cheat.
So yeah, this is something I'll get to on the next slide, but entanglement can also help to good provers to maybe prove things to you, more powerful statements than they could otherwise.
Okay.
Yeah.
So I don't understand this thing. If Alice answers yes, if Alice uses her qubit to answer yes, Bob could measure the same qubit and get that same answer.
Yeah, so Alice and Bob will have different qubits. So Alice has her own qubits, Bob will have his own
But they're
qubits.
entangled.
But they will be entangled, yeah.
So whatever Alice measures, Bob will measure the same thing.
Bob can perform whatever measure he wants.
But if he did,
Yeah, so if they decided to like measure if they had fully entangled qubits, so EPR states, and they decided to measure their EPR states in the same basis, then they would receive the same measurement outcomes.
so
But
whatever answer Alice gives, Bob could give the same answer.
This would allow them to sample a shared random string. But that's exactly what we were talking about earlier. Shared randomness doesn't help. So somehow there's an advantage for the two provers to sometimes measure maybe in the same basis, but maybe sometimes measure the different bases, and they get very different answers in that case. So yeah, there's more power here than just like simply fully correlating the measurement statement. So yeah.
The verifier is not asking Alice and Bob the question, is X in L? It's asking them some weirdo question.
Just some weirdo question, yeah. Yeah, I mean, it wants to know if X is an L, but it will accomplish this by maybe asking some other questions that are related.
Thank you.
Oh yeah, okay. All right, yeah, but like both of the Alice and Bob also know what X is, so they know what they're trying to convince the verifier. Okay. So again, the verifier is polynomial time, and let me just mention one consequence of the verifier being polynomial time, which is that all the messages sent, the questions and the answers, have to be encodable into polynomial and classical bits. Why is that? Well, I mean, the verifier can't write down a question longer than polynomial classical bits, but neither can it read an answer that has more than poly n bits. All right, and earlier I showed like the MIP interaction, just like a long conversation between the provers and the verifiers. But here I just drew a one-round protocol where they just ask one set of questions, get one set of answers, and that's it. And it turns out for our talk, it will be sufficient to consider one-round protocols. And for this class, there are like the standard completeness and soundness definitions and complexity theory. So when X is in the L, in the language L, that just means that there's some Alice and Bob who should be able to convince the verifier that X is in the L with probability equal to 1. So here we'll be looking at the perfect completeness case. And when X is not an L, so it's a statement that should not convince the verifier, that means that every Alice and Bob, no matter how malicious they are, should only be able to convince the verifier with probability at most, say, 1/2. And of course, this is like just any constant you want that's bounded away from 1. All right, so bounds on MIP star. Yeah, so let me again remind you that MIP we know is equal to NX. But what do we know about MIP? What do we know about MIP star? Pretend you didn't say that. It'll make this more interesting. Yeah, so exactly as Pravesh asked, it's not obvious if MIP star is more or less powerful. So typically, most people actually think that MIP star is like obviously more powerful because that gives the provers more ability, so maybe they can convince you of more things. But it also allows evil provers to convince you of more things. So it's not clear who does it help here. But in spite of that, in 2012, so 7 years ago, Ito and Vidick were able to show that MIP star contains NX, and therefore MIP star contains MIP. So MIP star is at least as powerful as MIP, so entanglement at least doesn't hurt you. But ever since then, no one's been able to show, does it help you though? Or maybe MIP star equals MIP. As for upper bounds, the best one we know is like quite embarrassing. So the best upper bound we know on MIP star is actually RE. So if you remember back to your like computability theory from undergrad, RE is recursively enumerable. So this is a class of problems that reduces the halting problem, including the halting problem. So as far as we know, MIP star, so two quantum provers, could conceivably convince you that a Turing machine halts. That's like within the realm of possibility right now. Let me say just yeah.
So is there some, like, one sentence intuitive takeaway why quantum doesn't hurt you, of the provers, or just not?
Yeah, it's, the one sentence takeaway is almost just it's because it doesn't hurt you. But if I can say a little more, what they did is they were able to take the classical protocol for MIP, the MIP equals NX protocol, and they worked really hard to show that every step in that protocol still works if the provers are quantum. So all the subtests that you run, you can't be tricked any better if the provers are quantum versus classical. Okay, so why do we only know RE as an upper bound? Why can't we get a better upper bound on RE? Well, let me just for like a second remind you, why do we know that MIP, so why do we have an upper bound on MIP without the star? So why do we know MIP is in NX? Well, how do you show an upper bound on MIP? The way you do it is you show that, like, suppose you had a problem that was in MIP, so it had a classical protocol with provers and verifiers, then you'd like to be able to simulate this protocol in a Turing machine. So you'd like your Turing machine to be able to maybe enumerate overall prover strategies and find if any of them convince the verifier to accept. And if one of them does, then you know it's a yes instance of the problem, and if none of them does, you know it's a no instance of the problem. And so what do you have to enumerate over in the classical case? Well, the verifier will give out an exponential, the questions are size polyns, or there are exponentially many of them. So prover strategy will be for each question, what answer do I give? And so that's an exponential size strategy. So you just have to enumerate over all of them, and that's how you get MIP equals NX. So how do you get an upper bound on MIP star? Well, what are the prover strategies here? So if you remember, the provers are allowed to share qubits, or entangled qubits, let's say. But we never put an upper bound on the number of entangled qubits they could use. So they could use maybe one entangled qubit, 2, 3, 4, all the way up to maybe an infinite number of entangled qubits. And so that means that there are like an infinite number of strategies for you to enumerate over. And you simply cannot do this in finite amount of time. Yeah, one more thing. You might hope that maybe like when you're asking the provers a very simple question, like when the input size of your question is very small, maybe the provers would not have to use a very large quantum state to convince you. But so far as we know, this is not true. Okay, that was a lot.
So can you give any even like very artificial example of some interactive proving system which would contain the halting problem?
That's what we're trying to do. But no. So yeah, this is like a big open question. Let's see if this is possible. Yeah. Like people really don't know the power of this class. Right.
I mean, not even this class, but even just for some arbitrarily defined interactive. Where the only constraint is that the verifier is classical. These other people I can, define all sorts of weird ways.
Yeah.
Quantum is just one thing that you could add to this.
Yeah.
Maybe MIP star where the soundness is just strictly less than 1?
Oh yeah, MIP star with a soundness is strictly less than 1. Yeah, contains the halting problem. So what does that mean? That means in the yes case, you always accept, but in the no case, you always reject with non-zero probability.
Sorry, so who's rejecting it?
So the verifier, in this case, the verifier, when X is in the language, you always accept. But when X is not in the language, no matter who the provers are, you always accept with probability at most 1/2.
I see.
In this other version, you always accept with probability in the no case that is strictly less than 1, but it can be arbitrarily close to 1.
I see.
So that was recently shown to be equal to. Or, yeah. It is. But yeah, that was recently shown to contain the multiprover. Right. So yeah, what's our result? Well, we add an E to the previous result. So we show that NEEXP, N double X, is contained in MIP star. So what is NEEXP? It's non-deterministic doubly exponential time. So it's a doubly exponential time version of NP, where the verifier is allowed to run in doubly exponential time. What does that mean? Well, that's time 2 to the 2 to the polygon. So 2 to the exponential. And one thing to know about this class, like by the non-deterministic time hierarchy theorem, it's strictly better than NX. And so as a result, we know that MIP star is strictly bigger than MIP, which means that we have like an exponential quantum classical separation in this case. All right, so what is a complete problem? For NEEXP, it's a problem called succinct recoloring. You probably all have guessed what it is already. So, just as you can have a circuit which succinctly represents an exponential time graph, or an exponential size graph, you can also have a circuit C which represents an exponential size circuit. So in the input to this problem, you're given a circuit C. It succinctly represents an exponential size circuit C prime, which itself succinctly encodes a doubly exponential size graph G. And given this circuit C, you want to know is G three-colorable. Okay. And so what's crazy about this is your graph is doubly exponential size, has doubly exponentially many vertices, which means to even name a vertex requires an exponential number of bits. So even to name a single vertex requires more bits than you have time to write down. And as a result, you don't even have time to check a single edge of the graph. And in spite of this, two provers who are quantum and all-powerful can convince you that the graph is resolvable. Okay, so that's kind of cool. And now, with all that background, I'm going to dive straight into the proof. So, any questions?
So the number of qubits required for this, is it finite or?
This is finite, but let's see. I think it is exponentially many. Any other questions? Great. Okay, so the proof. Well, I'm going to show you that n double x is contained in MIP star. But first, actually, I'm going to speak a bit about this prior result that nx is equal to MIP. And if you remember, this is like a purely classical result. So we're doing this kind of as a warm-up, but also because a lot of the technical things that are used in this proof will also be used in this proof for MIP star. So what does it mean to show that nx equals MIP? Well, this just entails giving an MIP protocol for succinct recoloring, which, if you remember, was an NX complete problem. So what does this MIP protocol look like? Well, the input is going to be this exponential size graph, which is, of course, encoded as a succinct circuit. And the verifier wants to know if this graph is succinctly three-colorable or not. So the natural thing to do is like, well, we only know one protocol. We only know one thing, which is to have Alice send the three-coloring to the graph G to the verifier. And maybe given this three-coloring, the verifier could read it and check that the graph is indeed three-colorable. Of course, this doesn't work, because the graph is exponential size, so there are exponentially many vertices, so this three-coloring, to describe it, would require exponentially many bits. So this is simply too long for Alice for the verifier to read in real time. Okay, but again, that's like the one thing we know how to do, so we'd like to do something that is somewhat like that. We'd like to find a way to get this to work in spite of this. And so what happens? Well, rather than the prover sending their entire three-coloring, what the provers will do is they'll encode the three-coloring that they have cleverly as a polynomial. Okay, so as a polynomial f, which maps fq to the m into fq. And what does this mean? Well, if you're not familiar with like finite fields or comfortable, just pretend it's the integers from 0 to q minus 1. That's fine for this one. And n here is chosen to be polynomial in n. So at the very least, to like describe an input to f requires only polynomially many bits. That's kind of good. And the way I'm not going to tell you anything about how you do this encoding, except to say that the way this encoding is done is a very clever encoding. You might know it as like the Reed-Muller encoding, also known as the low degree encoding. And the way it's done is such that if you're given one of these f's, and f is low degree, so it's a low degree function, a low degree polynomial, then it turns out it's actually very easy to check that it corresponds to a proper three-coloring of your graph. And when I say very easy, I mean that even though, again, it's an exponential time or exponential size graph, the verifier will only have to query maybe a few points at f to see if it corresponds to that three-coloring. And so the verifier will be able to do that in polynomial time. Okay, so if it's low degree, we're done, but maybe the provers could try to cheat us, because maybe they'll just give us a function which is not low degree. And then maybe we'll get tricked into thinking that it corresponds to a three-coloring in the graph. So the main task in this protocol is actually just testing that this function f is a low degree polynomial. And once you've done that, like I said, it's easy to check whether it corresponds to a three-coloring. Okay, so how do we test that a function f is a low degree polynomial? Well, you do it using something called the low degree test. And in this talk, I'll tell you about the line versus point pairing of the low degree test. Okay, so the line versus point low degree test. Again, your goal is to test that this function f, which maps fq to the m into fq, is low degree. And so you do this in a couple-step long protocol. And so the first step, you pick a point u in fq to the m, and another point v, which we call the direction. And this v is also in fq to the m. And the two of these will be chosen to be uniformly at random and independent of each other. And the first thing we're going to do is we're going to set L. So this L stands for line. And so L is going to be the line through u in direction v. So it's going to be the set of points that contains u plus tv for all t and fq. So it's like it contains u plus v, u plus 2v, and so on. All right, so now, having picked these points, directions, and the line L, the verifier will send the line L to Alice and the point U to Bob. Okay, so one crucial thing to know here is that the provers get partial information about the other provers' questions, but not complete information. So so Bob knows the point U, but there are many lines L that could go through U, and Bob doesn't know which one L's received. And Alice gets the line L, but there are many points along L that Bob could have received, and Alice doesn't know which one. And given the line L and the point U, the verifier just receives, Alice replies with an answer, and A, yeah?
What specifically do you mean by send the line out? Like send, for example, u plus tv for random t?
Yeah, there's just like a canonical encoding you can use, or this way will also work. Yeah. Okay, so given the line L, Alice will reply with some sort of answer. Given the point U, Bob will reply with some sort of answers, and I'm not even going to tell you what the format of the answers are. Actually, I will just in words, but it's fine if you ignore it. But the point of this protocol, the way that you design it, is that given these answers, the verifier can tell if f is low degree or not. Okay? Let me see what's coming in there. Okay. So yeah, you run this test, you give a line L, point U, give back answer A, answer B, and given these things, you can test if f is a low degree polynomial. And let me just briefly say, for those of you who are kind of in the know, how does the low degree test work? So what are the answers? So Bob is expected to reply with the evaluation of f at the point U. So he's supposed to send f of u. And Alice is supposed to reply with a polynomial g on the line L. So a low degree polynomial, degree d polynomial on this line L. And the verifier checks that Alice's polynomial g, evaluated at u, equals the value that Bob gave. So Alice checks that, or the verifier checks that g of u is equal to f of u. But if you don't understand that, that's fine, because for the rest of this talk, for our purposes, it's not important at all what these details are. It doesn't matter what the answers are, it doesn't matter what the verifier's accept condition is. All that matters is that this is the main subroutine in the NEXP protocol. So when you think NEXP protocol, just think line versus point test. And the questions that the two provers get are a line L and a point U. So that's all I'm going to tell you about NEXP contained in MIP. And are there any questions? Okay, so now let's move on to NEEXP.
I'm still amazed that this huge graph can be represented by a low degree polynomial. I mean, the kind of polynomial I would think of would simply have a zero for every answer. That would be too many zeros. High degree.
So the polynomial itself, its domain is exponential size. So inside the polynomial, like if you plug in various x's, you can actually recover the coloring of the graph. But the way this polynomial is designed is that the verifier just doesn't have to check all the x's. There's some other clever way of checking.
So there is this high degree polynomial.
Well, it's a low degree polynomial, but it somehow does encode all the information about recording. Yeah. All right. So now we want to show n double x is contained in MIP star, and this entails giving an MIP star protocol for our favorite n double x complete problem, which is succinct through color. All right. So here your input is a doubly exponential size graph, and encoded by this like very small polynomial size circuit. And you know your first idea, again, we only know one protocol, so can we use it? And what do I mean? Well, maybe we'd like the provers to encode their coloring in a low degree polynomial f, and then you run the low degree test to check that they're being honest, and so on. And so this looks like the following. The verifier is given one of these succinct through coloring instances, and it sends a line to Alice, the point to Bob, and gets back, answers from both of them and accepts or rejects based off of what it sees. But there are some kind of obvious problems here. So this protocol worked when our graph was exponential size, but now the graph is doubly exponential size. So kind of everything is blown up by an exponential. So in particular, when you do this, it turns out that this the messages that get sent end up being exponentially many bits, as does the verifier's runtime. Okay? So everything is exponentially bigger. And this is a problem, and the way we'll view it is as two problems, actually. So number one, we're going to say the questions are too long, and number two, the answers are too long. And we're going to solve both of these problems in different ways. Okay, so the outline of the proof is the following. We have this protocol, which I gave on the last slide, for succinct through coloring, but its questions and answer sizes are exponential. So we're going to fix this in two steps. Step one is called question reduction, which is where you bring the question sizes down from exponential to polynomial, though you leave the answers as exponentially long. And then in the second step, we answer reduce. So we also take the exponentially long answer sizes and reduce them down to polynomial. And step one is a step that involves the quantum. So this is why our protocol goes from being MIP to MIP star. And this is also the more interesting step. So step two is a bit more standard in the literature. So in this talk, I'm mostly just going to tell you about step one. Okay, so let's talk about question reduction. So our plan in question reduction is going to be the following. We want to delegate the sampling of the questions to Alice and Bob. Okay, so the verifier has to do a lot of work to sample these questions because they're exponentially long. So it can't do it, but someone's got to sample the questions. And conveniently, we've got these two all-powerful provers just sitting there. So let's make them do it. Okay, and so in this idealized protocol, instead of it looking like this, you would rather it look like this. Okay? In other words, Alice and Bob, you would like them to tell you the line and point that you would have asked them. So in this protocol, Alice is supposed to sample line L, and Alice is like, you would have given me this. And had you given me this, here's what I would have told you, here's my answer. And then Bob should also sample a point U that you would have given him, and then he will also reply with the answer. We call this introspection, this technique, because the provers are introspecting. They're asking themselves questions. And okay, first off, there are a million reasons this doesn't work. There are a million things that are wrong with this, but I'll get into that in the next slide. But this, at the very least, does require some source of shared randomness, because they both have to be able to sample these random lines and points which are somehow correlated. Okay, so how might we do this? What's a naive approach to this introspection? it's to give Alice and Bob a shared tape. So you know, Alice and Bob are sitting very far away from each other, but maybe somewhere in the sky you write out a shared random tape just containing as many random bits as they want. And Alice and Bob, they hear this random tape, and maybe they're supposed to interpret the first however many bits as a random point u in fq to the n, and then they interpret the second however many random bits as a random direction v in fq to the n. And it would be nice if Alice just looked at this random tape and told you the line through u in direction v. So, you know, u plus tv for all t. And it would also be nice if Bob told you the point u. Okay, and then they would actually tell you the line of point that they're supposed to sample. But, I mean, it doesn't work. And this shows that just shared randomness is not enough. And why doesn't it work? Well, there are like two separate reasons. So first, they could just lie. I mean, you have no way of checking them. Alice and Bob could look at the tape and tell you different line points. Okay? They could in particular tell you like a line and point pair that's very convenient. Like they could ask themselves easy questions. But not only that, even if they don't lie, there's another problem, which is that it's a shared random tape, so they both see the whole thing. So Alice can see Bob's point, and Bob can see Alice's line, which defeats the whole purpose of having two separate provers who don't know each other's questions to begin with. Okay, so what we need is some sort of better source of shared randomness, in particular a source of shared randomness that the verifier can control, and can enforce that these things don't happen. And this is where quantum comes in. So it turns out, I have a little battery.
John, there should be a power outlet on the podium itself.
Oh. Cool.
I don't know if it works, but
I think it doesn't. Okay, let's try the other one. Okay, let's try the other one on the wall.
is it plugged into your computer?
That's a good question. I think so. Something is not plugged in here. Let me see. Sure. Oh, that's a mic. Yeah. Can I try this? Yeah. Oh, there was a spark. Oh, thank you. Perfect. All right. Thanks. Okay, so what were we talking about? Oh yeah, shared randomness doesn't work, and so this is why we use quantum. So quantum states actually give you a form of shared randomness. So entangled quantum states give you a form of shared randomness. And what our protocol is going to do is kind of enforce that the provers share a very large entangled quantum state. And you know, we want to force them to have a very large entangled quantum state, and we want to have control over the entangled quantum state. So in particular, we want control over what state it is and how they interact with the state. And it turns out there are quantum protocols which allow you to do exactly this. So there are these protocols that are sometimes called self-tests, which can force the provers to, number one, share a specific quantum state, and number two, perform very specific quantum measurements on it. And when I say a protocol, I specifically mean like an MIP star protocol. So exactly the sort of thing we're looking at here. So in other words, like the verifier will ask the provers questions, get back answers, accept or reject based off of those answers. And these protocols have the guarantee that if the verifier accepts with probability very close to 1, then you can guarantee that the provers have to be sharing a specific quantum state, and they have to be performing specific measurements on it. So this seems promising. This is kind of what we're looking for. And we just have to hope that the state and the measurements that they perform on it somehow correspond to the exact distribution we want them to sample, this line versus point distribution. Okay, so what protocol do we use? We use something called the quantum low-degree test. It's a protocol that was invented by Natarajan and Vidick in 2018. This is the same Anand Natarajan who's like on this paper. It's a very cool protocol. You should hire him. He's a smart guy. And what does this protocol allow you to do? Well, it allows you to command the provers to share exponentially many entangled qubits. And it allows you to force them to perform two types of measurements. One that's called total x, and another one that's called total c. But not only that, it only requires, even though you're forcing them to do exponentially many entangled qubits, you only have a question size that's polynomial in A. Okay? And so this is exactly kind of what we're looking for, because remember, we wanted to sample the line and point. For us, these are both exponentially long strings. And so number one gives us that like an exponentially large source of shared randomness. But we also want the question size to be polynomial, much smaller. And this protocol also has that property. Okay, so what does all this stuff mean? Well, to understand it, you have to understand what qubits are, what X and Z measurements are. And I'm not going to tell you like what that means, but I will give you a toy model which basically closely approximates it, without you needing to know any quantum. Alright, so this is the toy model, which I will just call the EPR toy model. And, Alice and Bob are sharing maybe this entangled quantum state, but for now I'm just going to focus in on the Alice side. And with this entangled quantum state, this means that Alice has some like qubits that she operates on, but instead of thinking about qubits, I'm just going to imagine that Alice has something called the EPR box. And this EPR box, it has two registers, a Z register and an X register. And inside these registers are placed, in the Z register, string A in FQ to the M that's selected uniformly at random. And in the X register is a string B in FQ to the M, also selected uniformly at random. But Alice is not allowed to actually read these strings. Okay, so she's not allowed to directly interact with these strings. Instead, she's given another way of kind of peering into them and gaining information about them. And it's through these tables that will be written off to the right. These tables contain all of the dot products corresponding to A. So in the first entry, it contains like the number A.0000, and the second entry, it contains A.0001, and so on. All the way down to this, which should actually be like A.Q-1, Q-1. So in particular, if you have any string Z in FQ to the M, then there's going to be an entry in this table that tells you A.Z. And then she also has a similar table for the X dot products. So for any string X in FQ to the M, she can learn B dot X. All right, so these two tables are sitting right there in space. These are the things that she's allowed to read. And there's one rule constraining how she can read them, which is the following. So when Alice reads the cell A dot Z, you erase each cell B dot X such that Z dot X is not equal to 0, and vice versa. So if she reads in the X dot product table the cell B dot X, you erase each A dot Z such that Z dot X is not equal to 0. Okay, so if Alice wants to learn about her strings, it may look something like the following. Maybe she wants to learn, the Z dot product. And so then, after she does that, you have to remove all the cells in the X dot product table. Then maybe she wants to learn something corresponding to this X, which involves erasing some strings up top. Maybe she wants to learn something about X prime, and then you erase more strings up top. Okay, so that's what she gets to see. Let me give you a couple of examples just to see how this works. So suppose Alice were to read in the X dot product table the entry B.EI for each I. So in other words, she learns BI for each I, which means she just knows the entire string B. Okay? So what does she learn? Okay, so she learns the whole string B. Now, suppose she wanted to learn something from the Z dot product table. Suppose she wanted to learn something about A. Well, unfortunately, every non-zero Z has Z.EI not equal to 0 for some I. In particular, like, if it's not 0, there's some coordinate I which is not 0, and so Z.EI is equal to ZI. Okay? And so since she already read all the EIs in the X dot product table, that means she has to delete every Z in the Z dot product table. So every A dot Z is erased, and she doesn't learn any information about A. Okay, this thing right here is called a total X measurement, because she measures everything about X, she knows the whole string, and she doesn't learn anything about Z. And you can also define total Z measurements similarly. All right, example 2. Suppose Alice just reads the entry b.e1 from the x.product table. So this tells us she can't learn a.z whenever z1, the first coordinate, is non-zero. But she can read the entries a.e2, a.e3, a.e4, and so on. In particular, she can learn a2 through an. She can learn everything about the string a except for the first coordinate. All right, and in this toy model, so that's Alice's side, and Bob actually also gets an EPR box filled with the same A and B. So for example, if both of them do total Z measurements, they both learn A. If both of them do total X measurements, they both learn B. But if one does the total X, the other one does the total Z, then one will get A and one gets B. So sometimes, this allows you various levels of correlation between their measurements. All right, so I promised you that this kind of looks like if they hold entangled quantum states. So let me tell you a couple things about why this should look something like physics to you. So there are like three things about this model that make it look like physics. So number one, it kind of looks like it has entanglement because Alice and Bob do have some sort of shared information. Number two, it kind of exhibits this thing called the Heisenberg uncertainty principle. You may have heard about this from like popular science, where like if you have a particle and you learn its position, then you have to forget its momentum, and vice versa. And we have a similar thing going on. When you learn Z, you have to forget X. And finally, this has a property that's non-signaling. This is a property that any quantum theory must have. This doesn't allow Alice and Bob to communicate. It just allows them to correlate what they measure. Okay, so the summary thus far, using this quantum low degree test of Anand Natarajan and Ito and Vidick, you can force the provers to, number one, share these EPR and Q boxes. Number two, you can force them to perform total X or Z measurements. And you only require a question size of log n. And so in particular, you remember, we want them to share an exponentially many number of bits, and so m is going to be exponential, and so the question size will be all. And our goal is for Bob to sample a random point u, uniformly at random, and for Alice to sample b uniformly at random first, and then to sample the line that goes through u in direction b, without learning the identity of u. But to make it just easier for the talk, I'm just going to do it for a fixed b. Okay, so I'm going to imagine that Alice knows a fixed b in advance, and then have them sample the line and point, and I'm going to make it even easier just by looking at the b, which is a 1 in the first coordinate and 0s everywhere else. So we're going to look at lines with direction b equals 1, 0, 0, 0. And because we ran the quantum low degree test, we can force Alice and Bob to share their EPR boxes. To begin, I'm just going to suggestively rename the string in the first register to u instead of a. And so what the verifier is going to do is to tell Bob just to do a total z measurement. And Bob will learn the value of u. And this is just going to be the point that we're supposed to be using. Okay. So now we want Alice to learn the line L in direction, through u in direction b, without learning the point u. And we could just tell her to do a z total measurement, because she'd learn the line L, but she would also learn Bob's point u. So we have to do some sort of thing where we force her to remove some information. Okay. We want her to learn L, but not. So how are we going to do it? Well, it turns out that learning the line L, but not u, is equivalent to learning the values u2 through un, but not u1. And why is that? Well, every point in the line L agrees with u on positions 2 through m, but the points in L may disagree with u on the first position. Okay. So if she can learn this, but not u1, then she's learned the line. So our goal is to get her to measure b1, so the first bit of the x table, and also u2 through u1. Okay, and this is actually exactly what we saw earlier. So in example 2, if she learns b1, then she can still learn u2 through u1, but she's prevented from learning u1. So this is exactly what we want her to do. And now the one thing we have to do is, suppose she measures these and gives them to us and says, I've learned the line, but I didn't learn u1. We just have to check that she's acting honestly. Because, well, maybe she lies with her b1, or maybe she lies with her UIs. And we have no guarantee, because all we can guarantee is if we tell her to say z total or x total, she will act accordingly. But now we're asking her to do something different. So we have to prove that she's still acting correctly. And the way we do this is as follows. So we just cross-check her answer against Bob. So half the time, we're just going to tell Bob to do a total z measurement. We'll measure the entire string u, and then we just check her UIs against his. Because he's doing a total z measurement, he has to be acting honestly, and therefore she must be acting honestly too. And the other half of the time, we tell Bob to do a total x measurement, and check her B1 against his. And again, because he's acting honestly, so much she be. Okay, so that's the case of this direction. Yeah?
Did Bob already do a total v measurement earlier on and was fine you?
Yeah, so that's, I don't know, part of the narrative, but yeah, half the time really we'll be doing this, and half the time we'll be doing this. This allows us to check that Alice is working correct, or acting correctly, but then the half of the time that we get him to sample the z, the thing u, then one of them gets a line, the other one gets a point.
The other half of the time when Bob samples x, we just don't worry about what Bob says.
Yeah, that's just to cross-check Alice. Okay. Okay, so that was for the specific line B, but now let's do it for a general direction B. Just some arbitrary direction D. And again, the verifier will just tell Bob to do a z total measurement to receive the point u. And again, we want Alice to learn the line L through u in direction B, but not the point u. And it's just like a fun homework exercise that you can do at home if you want, which is that so long as we make Alice measure B.C from her X register, she still has all the information she needs to learn L, but this will erase the identity of Q. Okay, so that's question reduction. In summary, we use this introspection. So that's the first step. We use introspection, and this is where we make the provers sample the questions instead of the verifiers. And we use two properties of quantum mechanics theory. So number one, we use entanglement to jointly sample from the line versus point distribution. That gives us our shared randomness. But then we use the uncertainty principle, the Heisenberg uncertainty principle, to hide information about the other player's questions. And earlier I told you to imagine that this succinct three-coloring protocol was just the low degree test. It's not actually true. There's like a lot more that goes on. But similar ideas will work for the other questions in the succinct three-coloring protocol. And this establishes the first step of what we're doing, that n=x is in an MIP star with polynomial question size but exponential answer size. Okay, so in the time remaining, I'll just tell you a little bit about answer reduction and then a tiny little conclusion. So how do we do answer reduction? That's the second step. And after we do question reduction, our succinct three-coloring protocol looks like the following. Alice and Bob, they have their quantum now, they have shared states. In this protocol, the verifier will ask some questions, get back answers, and we have the guarantee that the questions are now poly n bits, even though the answers are